Welcome to Stats Land, the land of awesome stats. Yeah. Thank you for joining me today. Today we have a very special guest, as always, the brilliant, the one, the only, Chewbacca. Well, those are very, very nice words, Chewbacca. Thank you. We appreciate your joining us today. Thank you. So, HLM2, because we all need an extra week of confusion. So, let's wax on and wax off A. Like, really? Why would Mr. Miyagi say A? That's weird. So by the end of today, hopefully we understand what a random effects ANOVA is. We understand the random intercepts model, the random slopes model, the random slopes and intercepts model. We understand how to visualize mixed models in Pfeiffer, and we feel comfortable creating mixed effects, or mixed random and fixed effects models. So let's wax on and wax off, eh? So a little bit of data background. So if you have data that looks like this, well, here's the data set that we're going to be using today. This is the alcohol use data set, which you can load through the Pfeiffer package by saying data, open parentheses, alc use, ALCUSE, close parentheses, and that'll load the alcohol use data set. So the ID is repeated. So you'll notice that it goes 111, 222, 333, etc. And so anytime you see something like that, that's a good indication that there's going to be some, it's necessary to have some mixed modeling in there. And by the way, also if you look across the data set, the only things that change from time points from each individual time point, so basically the first three rows are the first person's measurements at time 1, time 2, and time 3. And notice that everything stays the same. For example, COA, which is child of alcoholic, they're still a child of alcoholic at each of the time points, and their gender doesn't change across the 3 time points. And their peer alcohol use, although presumably it could have changed, but for some reason it was only measured once. So those are things that don't change from time to time. Meaning that they can be modeled. Oh, I'm sorry. So if you look at age and age underscore 14, which by the way means how many years since they were 14 years old. And also alcohol use, those are the only things that change over time. So alcohol use is our outcome variable in this case. So the only thing that can be modeled as random effects are the things that change for each time point. So in this case, that would be their age. Because again, they're the only thing that differ at the quote-unquote nested level. So if we were to model, for example, the effect of being a child of an alcoholic, we can only model that as a fixed effect. And that'll make sense a little more as we go through. Also, we got C peer and C COA, which those are, C stands for centered. Don't worry about those. Basically, this data set came with some of the variables centered, which means we subtract each score from its mean. And then COA, again, child of alcoholic, and age underscore 14, like I said, is years since they were 14 years old. So here are some questions we might want to ask of this data set. 1, to what degree does alcohol consumption increase with age? And that's what I'm going to demonstrate for you. And then on your own, I'm going to have you try to identify which effect is strongest. Is it peer influence, age, or child of alcoholic? So with that, let's talk about a random effects ANOVA. So with a random effects ANOVA, we don't use any predictors. What we do is we just fit a grand mean and see if there are differences in means between the clusters. So in the image on the right, using that Donald, Hillary, and Obama data set, our clusters are Donald's measures, Hillary's measures, and Obama's measures. In the alcohol use data set, the clusters are each individual person. So we just fit a grand mean and see if there are differences between those clusters. And so notationally, what this looks like is, at least for the Donald, Hillary, and Obama example, we got performance sub ij, where I represents the ith measurement of person j, and that is equal to b sub 0j plus e sub ij. So again, we're just fitting an intercept, or really we're just computing a mean. And so and then below that, the second hierarchy of that model, B0J is equal to gamma 00, which is the fixed mean, plus U sub 0J, which is each individual person's deviation from that mean. So in this graphic, the top line there, the purple line is, I don't remember, I think that's Obama. Yeah, I'm pretty sure that's Obama's. So that is Obama's deviation from the fixed mean or the grand mean. It looks like Hillary was right at that mean, and then Donald was below that mean in gray there. So if you were to put all those together, then you would just substitute the gamma and the U for the B0 sub j, and you would get a full model that looks like that. So this is a random effects ANOVA model. Again, we're just fitting a mean across the different clusters and seeing how much people deviate from that cluster. And it's a great first step because we can see what proportion of the variance is due to individual variability, or in other words, sigma, which is our kind of universal symbol for standard deviation or variability, of E sub ij, which is the deviation, in this case, of like T1, T2, and T3, those deviations from the line, or the average deviation of each person to their respective average. So we can see what proportion is due to individual level variability versus what is due to cluster variability, and that's indicated by sigma of U sub ij. And what that represents is the variability of these lines from the average line. So we got two sources of variability here. We've got the deviation of the dots from their respective cluster line, and then we have the deviation of each of the line from the grand mean line or the fixed effect line. And then once we have these estimates, the sigma of E and sigma of U, we can compute what we call the ICC, which is the intra-class correlation, not the inter-class correlation, but the intra-class correlation, which is equal to sigma of U, which is the deviation, again, of the lines from the grand line, divided by that plus the deviation of the individuals from their respective line. And what this tells us is what proportion... Sorry about that. We had to take a little siesta. Moving along. Okay, so I believe where we last left off at was this point. So that last bit of code shows you how to plot in flexplot a random effects ANOVA. Each of the individual data points there in light gray are the observed scores at each of the time points for all the individuals. And how we make that happen is we say ALCUSE tilde ID. So ID will be on the x-axis and alcohol use will be on the y-axis. And then I jittered things just to make them a little easier to see. And then I just put jom underscore h line, which just adds a horizontal line to it at the y-intercept. So if we go back, the average, or the fixed effect here was 0.9220. Oops, I put 9330, but yeah, close enough. So that right there is the average among all people, or the fixed effect. And if you were to compute the ICC, fortunately for you, there is a function within Pfeiffer to compute the ICC, and no surprises there, it's just called the ICC, and then it takes as an argument the model where you are doing a random effects ANOVA. And so the ICC is 0.505, which means that 50% of the variability is attributable to the clusters. So there's definitely some need for hierarchical linear modeling in here. I'm not exactly sure what the design effect would be. Let's see. I forgot the formula. Let's see if we can do it in our head. So 1 plus 0.5 times n minus 1, so times 2. So 1 plus 0.5 times 2 is going to be 2 total. So the design effect of 2 means we would get statistical significance at half the sample size. That's how much our type 1 error rates are inflated. So definitely good thing that we're using mixed models here. Now we have the random intercepts model. So the difference between this and what we had before is now we add a predictor. So on the right, we've got anxiety on the x-axis and then depression on the y-axis. So we allow the, in this one, when we say random intercepts model, we allow the intercepts to vary between clusters. So, in the figure on the right, we've got doctors, each with their individual clients. And so the idea is that we allow each doctor to have its own intercept, but the slopes are fixed. So every of those lines are parallel because we made them that way, or we forced them to be that way. So if we were to look at this notationally, we would say depression subscript ij is equal to b sub 0 j, indicating that the intercept is a different value for each level of j, in this case doctors, plus b1 times anxiety. Notice there is no subscript for the slope other than the 1. But there's no j for the slope there. And then e sub ij. And then the lower level of that model is b sub 0j plus gamma 00. So we got a fixed effect, which is represented by the intercept of the red line. And then plus u sub 0j, indicating everybody deviates from that. So taken together, that's how you do it, y'all. Now how do we do it in R? Like this. So again, LMER, linear mixed effects regression, and then alcohol use tilde1. We actually don't need the tilde1. It's assumed that you're fitting a intercept model. Although I think you had to do it in the last one. If you don't have any predictors, I think you have to put a 1. Could be wrong, but I think you have to put a 1 if there are no predictors. But if there is a predictor, you don't need the 1. So anyway, the left side of the parentheses area is the same as before, except we have age underscore 14. And on the right side, it looks exactly the same, except it means something different. Before that, one given ID meant every person has their own mean. But in this case, we're saying every person has their own intercept. So identically, it looks the same in there, but just psychologically, slightly different interpretation. And then we can look at the summary or the estimates, and it's going to give us some output like this. And so again, like before, there is a random effects category and a fixed effects category. And under the random effects, it shows that the variability about the intercept is 0.5966. So on average, people deviate from the grand intercept or the fixed intercept by, oh, well, that's the variance. So on average, and right next to it is that 0.7724. So on average, people deviate from the number of alcoholic drinks by approximately 3/4 of a drink. And then the 0.4915 is the variance, the residual variance, or how much the dots deviate from their respective lines. And then under the fixed effects, we have 2 of them. We have intercept and we have age. And those are common among everyone. And then if we were to plot it, by the way, y'all owe me big time for this one. That was kind of a pain to write. But this is kind of a function that uses the flexplot function. It's called mix.mod.visual because it's kind of tough to visualize mixed models because everyone has their own individual slope, but you still want to visualize things. And so my idea is to basically randomly sample within the IDs show the fixed effects, and then show the random effects for each of those IDs. So in this case, we've got 6 IDs. I think that's what it defaults to. I don't remember off the top of my head how you change the number of people it randomly selects, but y'all can look that up somehow. Well, you know how to look it up. Just put a question mark in front of the command. So anyway, same notation as flexplot. The only addition is that you add the model that you wrote before, and it will extract from that the fixed effects and the random effects and then plot them on graphics. And so that's what you see on the right. And notice how each of those gray lines, which are the random effects slopes, so each of those lines are parallel, as we would expect, because this is a random intercepts model, not a random slopes model. And notice that they approximately go through where you would expect them to go through usually. So yeah, no serious concerns there. This would be really good if we had like lots and lots of data points for every individual, and we might, like, for example, have some non-linearity issues. It would be nice to have this sort of graphic to tell us if that's going to be a problem, but it looks to me that it's not a problem here. On average, it seems that people are drinking more as they get older, which makes sense. And actually, what are the fixed effects? So age underscore 14, so 0.27. I think this is like drinks per week or something like that. So on average, every year from the time that they are 14, they increase in a 0.25 drinks per week from the ages of 14 to 15, 16, 17, whatever. It's 3 years, yeah, 3 years. So 17. So that's how you can visualize it in R. Wahoo, that's exciting. Yay. Now we go on to the random slopes model. So for the random intercepts model, the slope was fixed and then the intercept was able to change, whereas in the random slopes model, it's the opposite. The slope is able to change, and it would be unusual to have something like this, but it could happen. So in this example, the notation would be depression sub ij is equal to b0. Notice there's no j subscript under the b because, again, everybody gets the same intercept. And then we have b1 sub j, indicating everybody has their own slope, or every cluster has their own slope, times anxiety plus e sub ij. And then at the second level, we've got b1 j equals gamma 1 1. You know, before I called it gamma 1 0. So I think it's actually supposed to be gamma 1 0, but you get the idea. So that is the fixed effect of the slope. And then u sub 1j indicates everybody deviates from that slope. And then taken together, that's what it looks like right there. So how do we do it in R? With magic! Like that. Now you have to kind of do something funky, so it looks very similar to the other model. The only difference is right here on the right hand side within the parentheses. So now we add age underscore 14 to indicate that the slopes are varying for every given ID. But we also have to do something funky. We have to put -1, and -1 is the way that you tell R not to fit an intercept. And so here we are saying do not vary the intercepts for each of the IDs. So it's kind of funky how you have to do it that way, but that's how you have to do it. And then if you were to study the estimates, you would get something like this. And under the random effects, we've got the variance is 0.22 and the standard deviation is 0.47, indicating that the variability about the slope is 0.4717, meaning that we have, for example, in this case, everybody's slope is 0.27, so on average, people are increasing the amount that they drink by 1/4 of a drink per week, but you would expect them to deviate from that slope by, some people are deviating more or less from that, and the degree to which their slope changes is 0.47 drinks per year, if that makes sense. So that is that, and then to plot it, oh, where'd my plot go? Oh. Anyway, that's how you would plot it. So, oh, we're going to pretend this was intentional and say, I didn't want to spoil it for you, my young statistical Padawan, so I want you to find out what it looks like. Yeah. So, do it. Pause the video and stuff. Oh, yeah. No, I did it. Ha ha, just kidding. Okay, I'm going to pretend that whole thing didn't happen. Okay, one thing I just wanted to compare is if we were to look at the fit of the two models. So the one on the right, let's see. Both have the same fixed effects. The only difference is the random effects. Okay, so on the right is the random intercept model. On the left is the random slopes model. And what I wanted to point out here is notice the residual variance. So that's the same as if we were to do a regular regression. You know how sigma was the deviation from the predicted line? Exact same interpretation here. It's the deviation of each individual's dots from their respective lines. And what we find on the the random intercepts model with a fixed slope model is that the deviations from their respective lines are much larger on the right side than they are on the left side. So if you were to go with one or the other, you would probably choose to go with the random intercept model. That one fit a whole lot better. And if you actually look at the next graphic, look at that. I was on the ball, people. Things are a little wonky because again, you have to make sure that the intercept is exactly the same, and the only thing that can deviate is the slope. And at least for this data set, it's a lot harder to fit that when you have to fix it at the same intercept. And so things get a little wonky, like this one. No matter every single data point, we are under predicting how much they're going to drink, and that's just kind of the nature of fixing the intercept. And likewise, this one, we are overestimating every time. So not the best model, and it's kind of cool to be able to see that visually and say, hey, this ain't a good model to fit. So yeah, but notice the, so you see that the intercepts are fixed, slopes are different, and yeah, that's the random slopes model. So now we've got the random slopes and intercept model. So this model allows both the slopes and the intercepts to vary randomly across clusters. And so there's the notation for it. Notice we've got subscripts of j for both the slope and the intercept. And we also, at the level 2 area, we've got a fixed effect for each of them, and then of course randomly varying from that. And then we've got it taken together. And then on the right is a graphical representation of that. Notice how neither the slopes nor the intercepts are fixed, and everybody's allowed to deviate as they please. And we would expect this model to fit better than the other two, again, because you're given flexibility to let everyone have their own fit. And no surprises here on the notation. So the only difference between the last one is we don't have that -1 within the parentheses. And so that will default to letting all the intercepts and the slopes vary. Well, it'll, again, without the -1, it'll default to have all the intercepts vary, but now we're adding the slopes for age_14. And then if we were to study the estimates, that's what they look like. So again, under the random effects, notice we have a random effect for the intercept, a random effect for the slope, and just like we always do, we have a random effect for the residual. Now remember, last time the best we had was 0.55, and not surprisingly, we decrease the amount of residual variance down to 0.3373, which is what we would expect. And then below that are the fixed effects. So the model is predicting that at age 14, the average person will drink on average 0.65 drinks per week, and they will increase by an average of 0.27 drinks a week for every year that they age. And one more thing that I've ignored up until now is that bottom thing that says correlation of fixed effects. What is that? That is the correlation between the slope and the intercept across the individuals. So notice it's negative. So basically what that means is if you are one of the people who has a small intercept, meaning at the beginning of the study, when age is 14, because that's our 0 point, at the beginning of the study, you had a small number, which meant you drank very little. What that is saying is that for those who have small intercepts, they tend to have large slopes. So if you started out not drinking much, the model predicts that you're going to have a higher rate of increasing your drinking than somebody who starts out high, and that actually makes perfect sense. That if you're really high to begin with, you're probably not going to get much higher, but if you're low, you have plenty of room to grow. And that's basically what that correlation of fixed effects means. And then, I already mentioned this, but before, again, the residual variance is 0.4915, now it's 0.3373. Of course, the random intercept and slope model is going to fit better. And then that's how you would visualize. Again, same thing. Notice how nothing's changing. The only thing that's changing is that part right there, which is the model that you fit. And by the way, at this point, and probably for the foreseeable future, you can only have one predictor in the mixed model visuals, because it would just get super complicated to do additional panels and different lines, like for the treatment group versus control group. But just for now, it's just one variable. So if you're visualizing this and you have multiple variables, you have to do one variable at a time, basically. And then again here, the gray lines, each of them has a different slope and intercept. And if you look at them, it looks like they're doing pretty good. Now, one thing that's interesting about this is you might say, hey, dude, we got a problem here, okay? This model is under-predicting individual 15 every single time. Shouldn't it be a best-fitting line like in regression? Shouldn't it like have some over-predict and some under-predict? But no, dude, all of them are under-predicting here. I got a problem. And then you storm out of the room and then you get angry. Yeah, so moving on. Okay, I'm just kidding. I'll go ahead and answer that. So the reason why this is because what happens with mixed effects models is it will always bias these individual lines to be closer to the grand mean than they would otherwise be. So notice that if you were to do a straight up regression, it would have a line that goes approximately right there through the center of the data points. But what it's doing is it's actually making it a bit more conservative, because it's accounting for the fact that you belong to a data set where we have a fixed effect. And so it's going to kind of average them a little bit. So it's going to take the regression line, just a regular regression line for you, and then it's going to kind of sort of average it with the fixed effect line from the mixed model. And it's going to bring it a little closer to that line. So the idea is that if you have one person that is just a huge outlier, it's not going to heavily influence what's happening. It's going to always default to being a little more conservative than the individual regression lines will be. Hopefully that made sense. But overall, it seems to be doing pretty good. And a little more, and here's another example in 70. If you were to do just a standard regression, you would have a much steeper slope there. But again, the mixed model has kind of mitigated that a little bit and made it a little more conservative. So that is the random slopes and intercept model in R. So in summary, with fixed effects, those are effects that are common among all clusters. For example, they might have a common intercept or a common slope. Well, I guess they would have both. If you have a predictor, they're going to have a common intercept and a common slope. The difference is whether they will also have random effects or not. So and that's kind of the next point. All random effects should have a fixed effect. So for everything that you specify, there is a random effect for this slope or for this intercept. Well, it also has a corresponding fixed effect.
And I have never seen otherwise, and I don't think it makes sense anyway. So hopefully that just made sense, what I just said. Every time you have a random effect, there is a corresponding fixed effect with it. Or another way to think about it is when you do a model, you're going to have random effects, which indicate that... I'm just losing my train of thought. All right. Any questions on that? Let me know. And then random effects, we include a random effect when you suspect that... No, that's a word. I looked at it and I was thinking, is it suspect or suspect? Isn't that funny how that works sometimes, that you just forget how to speak English when you've been speaking it your entire life? Oh, never had that problem? Happens to me all the time. Okay. Yeah. Suspect. I think that's the word. Why does it sound so weird now? So you include a random effect when you suspect clusters will deviate from the common effect. So do you expect your cluster to have different slopes? Then add a random effect for that slope. Do you expect your clusters to have different intercepts? Then you better add a random effect for the intercepts. Typically, we don't add random effects for an experimental condition, by the way. That would say that the treatment effect, for example, the difference between the treatment and control group, is varying in its effectiveness across therapists. That might make sense occasionally, but typically we don't do that. And let me think about that a little bit more. Let's see. Okay, I'm going to modify what I just said. We actually don't add random effects for an experimental condition, because you remember how I said earlier, which is actually the very last bullet point there, that everything that is common among the data set, so going back, okay, right here, you remember how I said male has to be a fixed effect because it doesn't vary between time points. And likewise, unless it's some sort of a repeated measures design where they're exposed to multiple experimental conditions, you actually can't model the experiment as a random effect. Again, unless there's an experimental condition, in which case you actually would do that. So, sorry for that. See what happens? I wrote these a year ago, and I have learned things since then. Learning's good. You should always learn and stuff. All right. So scratch that bullet point. Okay, and then the last one, random effects have different values in the data set, which is what I just showed you, while fixed effects repeat themselves. So, how shiny is that waxed model, dude? That doesn't make... Okay, so first Mr. Miyagi was saying A, now he's saying dude. Whatever. So the objectives were to understand random effects ANOVAs, random effects, or random intercepts model, random slopes model, random slopes and intercepts model, visualizing mixed models in Pfeiffer, as well as feeling comfortable creating mixed random and fixed effects models. And with that, people, thank you for joining me on this lovely, lovely day. Hope you have enjoyed yourself. Special thanks to our guest who has oddly remained silent the entire time. But I'm very fortunate that he came back for the re-recording of this video on day 2. Ladies and gentlemen, please give a final round of applause for Chewbacca. No, it's been our absolute pleasure. Thank you, Chewbacca. Peace out.